Hello everyone, welcome to the session on previous year questions of ISRO exam from digital circuits of ECE and EE. Myself, I am Pavan Kumar Reddy, faculty of ACE Engineering Academy. Let us see how we got questions on digital circuits in ISRO exams. Let us see first question. Minimum number of complementary CMOS transistor pairs will be required to implement function f equals to ABC plus A plus B plus C whole bar. So, let us rewrite this function ABC plus A plus B plus C whole bar. So, I can rewrite it as ABC whole bar and with A plus B plus C whole bar. Because always we need to get a function which is represented in complementary form when you are implementing in complementary CMOS logic. So, if you are observing this ABC whole bar requires minimum number of 3 pairs of transistors, then A plus B plus C is required, then A plus B plus C whole bar requires 3 and complementary of that, so it requires 4 number of pairs. So, ABC bar is required 3 number of pairs of CMOS transistors and A plus B plus C requires 4. Now, once we are getting these ABC whole bar, A plus B plus C, what is required now? If I say it is P, it is Q, now I need to implement PQ whole bar. For this requires another 2 pairs. So, finally, 3 plus 4 plus 2 is equals to 9 pairs of CMOS transistors. So, what is it here? ABC plus A plus B plus C whole bar we have written as ABC bar and with A plus B plus C whole bar. So, ABC whole bar requires 3 pairs, A plus B plus C whole bar requires 3 pairs, A plus B plus C requires 4 pairs. So, after that it is P, it is Q. If I say PQ whole bar we need to implement. So, it requires 2 pairs. Finally, 3 plus 4 plus 2, it is 9 pairs of transistors required to implement the logic function. So, answer is D. Right. Now, let us see next question. The CMOS circuit shown below implements the function. So, implementation is given, we need to find the function which is implemented. A very simple logic we can apply. First, we can observe pull down circuit. In that, if you are observing a transistor A is logical OR with B and this entire is logical AND with C, this entire is logical AND with logical OR with D. So, if you are observing these two are parallel, which is saying that A plus B, right, is in series with C and with C, and this entire is logical OR with D because it is in parallel. So, finally, we are getting this function complement. Complement of this function is implemented. So, observe correctly. Just observe pull down circuit, pull up circuit is obviously dual of that, it is implemented in complementary CMOS logic. So, if you are observing that A, B are in parallel, which is logical or A plus B, this parallel connection is in series with C, so it is logical AND with C. This entire is logical OR with D because it is in parallel, so A plus B AND with C plus D whole bar. So, answer is C. For this question, answer is C. Let us see next question. The output frequency of decade counter that is clocked from 50 kilohertz signal is. A decade counter is nothing but mod 10 counter. When it is mod 10 counter, frequency is obviously divided by modulus of the counter. So, frequency of clock given is 50 kilohertz. when you say it is mod 10 counter, so F dash is going to be FCLK divided by modulus of the counter. Then 50 kilohertz divided by 10 is going to be 5 kilohertz. Right, answer is C. Once again, if it is a mod 10 counter, why it is mod 10 counter? It is a decade counter is nothing but a mod 10 counter. So, it is clocked with 50 kilohertz. So, we need to calculate the output frequency, that is nothing but the frequency or clock we are supplying divided by modulus of the counter. So, F dash is going to be F clock divided by modulus is 10. Obviously, 50 kilohertz divided by 10 is 5 kilohertz. Answer is C. Now, let us see next question. How many number of off-adders are required for m-bit number addition? I think it is missing. So, how many number of off-adders required to implement m-bit adder? M-bit adder. So, as per our earlier discussions, if you observe that, if I say simply A3, A2, A1, A0 and also B3, B2, B1, B0, then assuming there is no input carry, then what we can say here, in A0, B0 position we need to produce S0 and also carry C1. So, A0, B0 position needs just off adder, because it is accepting only two inputs A0, B0, which produces some S0 and also carries C1. In this digit position or in this bit position, we need to use compulsory full adder, because it is required to add C1, A1, B1, which requires a full adder. So, it is off adder, it is going to be full adder. Then here it is producing S1 and also carries C2. In this digit position, again we need to use full adder, compulsory, because it is adding C2, A2, B2, which produces S2 and also carry C3. So, in this digit position or in this bit position, C3 plus A3 plus B3 is producing S3 and C out. Then in this position also it must be needed to use full adder. Final confirmation is optimal implementation of this 4-bit adder requires 1 off adder plus 3 full adders. For 4-bit adder. If I say n-bit adder, 1 off adder plus m minus 1 number of full adders. Then what we get here, each full adder can be represented or implemented with 2 off adders and 1 2 input OR gate. So, 1 off adder plus 2 into m minus 1 off adders, because each full adder needs 2 off adders. So, what we can say here, 1 plus 2m minus 2 off adders, it is going to be 2m minus 1 number of off adders required. So, what is it here? 1 off adder, n minus 1 full adders required to implement m-bit adder optimally. So, each full adder requires 2 number of off adders. Obviously, 1 off adder, 2m minus 2 off adders is finally 2m minus 1 off adders required. Option is A. It is an optimal implementation. Let us see next question. It was given in electrical ISRO exam. So, what is the output of XOR gate with A and B as input? So, XOR function, 2 input XOR function, if you write, so Y is equals to A XOR B. If I write truth table 0 0 0 1 1 0 1 1, output is going to be 0 1 1 0. If I write a SOP expression of A XOR B is equals to AB 0 1 output is 1, A bar B, AB 1 0 output is 1, A B bar, which is a SOP expression. If I write POS expression observing max terms, AB 0 0 output is 0 means it is A plus B, Another one is AB11 also output is 0, which is A bar plus B bar. So the POS expression, if you rewrite, it is A plus B and with AB whole bar. So answer in this is C. A plus B and with AB whole bar. The XOR function also can be expressed as right, A plus B and A bar plus B bar, which is POS form, and SOP POS are functionally same. So A bar B plus A B bar is SOP and A plus B and A bar plus B bar is POS form. This A bar plus B bar also can be written as AB whole bar. A plus B and AB whole bar is also right XOR function it is representing. So answer is C. Now let us see next question. Right. A bulb in staircase has two switches. One switch being at the ground floor and the other being at first floor. The bulb can be turned on and also off by any one of the switch irrespective of the state of other switch. The logic of switching of bulb resembles. Here it is mainly depending on enable and disable input. What it is saying here? Here is irrespective of one switch using another switch, it must be possible to switch on as well as switch off. So once again, so the entire data is given is there are two switches and irrespective of position of one switch using another switch, it must be able to switch on and switch off. Is nothing but the switch should not be disabling other input. A simple logic is the position of the switch or any one of the input should not be disabling other inputs. That is required function. So once again, what is that here? So it is having two switches, one is at ground floor, one is at first floor. Irrespective of position of one switch, it must be possible to switch on or switch off. So then it should not be disabling the logic gate for other inputs. There should not be any disable input. So if you are observing that AND gate, if I say AND gate, for example, if one is off, one switch is off, irrespective of other switch, it is going to be off always. I am unable to switch on with another switch. So AND gate is not suitable. Once again, so if one input is 0, logic gate is disabled or the other switch is getting disabled. So irrespective of other input, it is going to be off always. So if I take OR gate also, example OR gate, if one input is 1, irrespective of other input, output is 1. That means if one switch is on, irrespective of other switch, it is going to be on always. We cannot switch off. So coming to NAND gate, if I say that one input is 0, irrespective of other input, output is 1. Means if one switch is off, by using other switch, it is not possible to switch off at all. But coming to XOR gate, a simple logic, coming to XOR gate, so using that, if one input is 0, output is A. That means by using this A switch or another switch, you can switch off as well as switch on. So if A is 0, it is going to be 0 means off. When A equals, it is going to be 1 means it is on. So when it is 0, it is possible to switch on as well as switch off. Coming to XOR gate, if one switch position is at logic 1, another input is A. Then what we get here, output is A bar. By using A switch, again it is possible to switch on as well as switch off. If A equal to 0, A bar is 1 because output is 1, that means it is on switch. So when A equals to 1, output is 0, you can switch off. So XOR gate can be used to get expected function because irrespective of position of one switch, using another switch, it must be possible to switch on and switch off. That means there should not be any disabling condition, either logic 0 because XOR gate is enabled for both logic 0 and logic 1. There should not be any disable input. If it is disabling, other switch is not functioning. So, any one of the input is able to disable the logic gate, it is impossible to control the output using another switch because it is getting disabled. That means there should not be any disable input. The logic gates we have XOR gate as well as XNOR gate also can be used to get this function, which is nothing but a dual switch which we have been using in regular applications. So, answer is XOR gate for this question. Answer is B. Now, let us see next question. Right. So, which was given in ISRO exam, EC paper. If input to T flip-flop is 200 Hz signal, then what will be the output signal frequency of 4 T flip-flop are connected in cascade? A simple thing is, it is saying that 4 flip-flops are connected in cascade. So, let me take here T0, Q0 are connected to one, there is a clock. Then again one more stage, here we can say T1, Q1, Q1 bar. So, Q0 if I take clock T1 is equals to 1, and third stage I can say here T2, Q2, Q2 bar, T2 connected to 1, Q1 is also clock. Then one more stage, what do you get here? T3, Q3, Q3 bar, and T3 is connected to 1, Q2 is clock. So, if you observe clearly, as T0 is connected to 1, if I say it is a frequency F, here it is going to be F by 2. One flip-flop is toggling at every clock edge occurrence, is saying that the clock period is doubled and frequency is halving. So the clock we are supplying to the second stage is F by 2, ripple counter. So, output of this is used as a clock, output of this is used as a clock to the next stages, output of this is used as a clock for next stage. So, we are using cascading stages. Then what happens here? So, if I say frequency after fourth stage, it is going to be F by 16. So, 200 Hz divided by 16, that is the frequency of last stage. So, it is going to be 4 4s are 4 5s are 50. So, it is 50 by 4 means it is 12.5 Hz. Answer must be 12.5 Hz. So, it is missing in the options, so we can choose none of the above. Right? Answers given are not matching with the frequency we are getting after fourth stage is 12.5 Hz. So, answer is not there in the given option, so we can choose none of the above. Right? Let us see next question. Right? Simplify the below function represented in sum of minterms. So, it is given a 5 variable function, you need to minimize this. So, let us see how we can do a 5 variable function minimization using K-map. Let me take here a 5 variable K-map and marking minterms. Then let us see what we get minimal expression. If I say that A, B, C, D, E, let me say it is for A equal to 0, the green one, the white one is for A equals to 1, and remaining variables we are using B, C, D, E. So, here it is 0, 0, 0, 1, 1, 1, 1, 0, and here also 0, 0, 0, 1, 1, 1, 1, 0. Now, this is a 5 variable K-map. In this, let us mark minterms specified. So, what is that here? Sigma m of 0, right? 0, 1, 2, 3. Next, 8, 9. So, 8, 9. then we are getting 16. So 16 in A equals to 1 K map, 0 to 15 in A equal to 0 K map, and from 16 to 31 in A equals to 1 K map. So when it is 16, it is, this is the position, it is 17, then 16, 7, 18, 19, then 20, so it is going to be 20, 21, 22, 23, then 24, 25, 26, 27, 28, 29, 30, 29, 30. So once again, if you are observing, 31 is there, 30, 31 is there, right. So this is a K map we are getting. Now let us group to find a minimal expression of this. If you are observing clearly, so there is an octave in A equals to 1 K map. It is an octave in A equals to 1 K map. And also here we have an octave both from A equal to 0 and A equals to 1. Let me mark, it is an octave. It is an octave. And also there is a quad in A equal to 0 K map, and there is a quad in A equals to 1 K map. So 2 octaves and 2 quads. If you are observing, one octave is only from A equals to 1 and another octave is from both A equal to 0 and A equals to 1. There is a quad from A equal to 0, there is a quad from A equals to 1. Now let me write expression here. So if I write expression here, so here it is going to be, right, BC are changing, A equals to 1 is not changing, so it is right in A equals to 1 K map, so it is A, and here BC are changing and only D equal to 0 is not changing, so it is A D bar. Then another octave is there from both A equals to 0 and A equals to 1. In this, what is that here? C bar is not changing, and here it is D bar, C bar, D bar. Plus, there is a quad from A equal to 0 K map, A equal to 0 K map, A bar, B bar, C bar, plus another one is from A equals to 1. So it is A, B, C, A, B, C. So if you are observing correctly, right, A D bar plus C bar D bar plus A bar B bar C bar plus A B C. So if you are observing this A D bar, it is C bar C plus D whole bar, A bar B bar C bar. Again here A bar plus B bar plus C bar whole bar is nothing but A B C. So correct answer for given question is option A. Once again, so observing that, are they from both A equal to 0 and A equals to 1, or only from A equal to 0 or A equals to 1? If you are observing that this octave is from only A equals to 1 and BC are changing, D equal to 0 is not changing, A D bar, and another octave from both A equal to 0 and A equals to 1 means A is changing, should be eliminated, and also here C equal to 0 is not changing, C bar, D equal to 0 is not changing, D bar, C bar, D bar, and this quad is only from A equal to 0, so A bar, B bar, C bar which are not changing, A bar, B bar, C bar, and another quad from only A equals to 1, so A is 1, A is not changing, and BC 1, 1 are not changing, ABC. So finally, if I observe the given options, it is given in a different way. C plus D whole bar is nothing but C bar D bar. A bar plus B bar plus C bar whole bar is nothing but ABC. Finally, the answer is A for the given question. Let us see next question. Which of the following statement is true for programmable logic array? Programmable logic array. See, when we have that a ROM implementation, we can have a PROM, PLA and PAL. So here we can say that AND OR, right. So in PROM AND is fixed, OR is programmable. or is programmable. And in PLA, AND is programmable, OR is also programmable. And in PAL, AND is programmable, OR is fixed. So, in the given, it is asked about PLA, in that both AND is programmable, OR is also programmable. So, which one should I choose here? Programmable AND and programmable OR. Answer is C. In programmable logic array, AND is programmable, OR is also programmable. Now, let us see next question. What is simplified Boolean equation of a logic circuit if the circuit output is 1 for following inputs? So, if you are observing that ABCD 0 0 1 0 function is 1, which combination is that? It is 2, and ABCD 1 0 0 it is function is 1 means it is 8, and here ABCD 0 1 1 0 function is 1 means it is 6, ABCD 1 1 0 0 means it is 12 for these. So, finally, what we can say here, f of a comma b comma c comma d is equals to sigma m of 2 6 8 12, 2 6 8 12. Let me take K map to simplify given function. So, variables are A, B, C, D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So, 2 is minterm, here 2 is minterm, 6 is also minterm, and 8 is minterm, 12 is also minterm. Then, if you are observing the grouping, this is one grouping, this is another grouping. So, this is resulting A bar, C, D bar. Here in this A equal to 0 is not changing, C, D are not changing, A equal to 0, A bar, C, D 1, 0, C, D bar. Another one is A equals to 1 and C, D 0, 0 are not changing, plus A, C bar, D bar, A, C bar, D bar. So, A bar, C, D bar and logical OR with A, C bar, D bar. Answer is A. Once again, the given, if you are observing, so for these combinations function is 1 means the minterms are 2, 6, 8, 12. Using those, if you are simplifying, A bar, C, D bar plus A, C bar, D bar, answer is A. Let us see next question. When transistors are used in digital circuits, they usually operate in the dash. See, when we are using the transistors, that is bipolar junction BJTs, then it can be DTL, RTL, TTL. In all these, if you are observing correctly, so either it will be in a cutoff region or saturation region. When transistor is on, it is pushed into the saturation region. When it is off, it is into cutoff region. Except in emitter coupled logic, in every bipolar logic family, the transistors are used either in cutoff or saturation region. So, depending on transistors, we can say this. See, when we are saying that bipolar junction transistors, so it will be operated either in cutoff region or saturation region. In emitter coupled logic, it is switching between cutoff and active region. So, here excluding that ECL, so in all other logic families, bipolar junction transistor will be operated either in saturation or cutoff region. And next, when we say that CMOS logic family, it is not mentioned which logic family is that. If I say that MOSFET, it is a FET, then obviously transistors will be operated either in a cutoff or linear region. In steady state conditions, MOSFETs are going to be either in a cutoff or linear region. When it is transitioning, it is possible to see transistor is in saturation region. But when steady state conditions, if you are observing in CMOS logic family, either in cutoff or linear region. But from the given, assuming that it is bipolar junction transistors, right? Answer we are choosing is C because it will be in saturation on cutoff region. Now let us see next question. The gray code for A5 hexa is equivalent to. So what is given here? A binary information is given. We need to find what is a gray code equivalent. So if you know that Bn minus 1, Bn minus 2, Bn minus 3, so and so, B2, B1, B0. Then what we can say here, when you are converting binary to gray, MSB as it is and take XOR of successive bits to get remaining bits. Again XOR of these two will be resulting Gn minus 3, so and so. Again XOR, and here it is G2. Again XORing these two will be resulting G1. Again XORing these two will be resulting G0. So whenever it is required to convert binary to gray conversion, MSB as it is, to get remaining bits, take XOR of successive bits. What is it here? Given is A5. So A5 equivalent to A is 1 0 1 0, 5 is nothing but 0 1 0 1. Now I need to get a gray equivalent of this binary. So it is given that gray code for A5 hexa is equivalent to. So let me do that MSB as it is. Then take XOR of these two is resulting 1. XORing these two is resulting 1. XORing these two resulting 1. XORing these two resulting 0. XORing these two is 1. XORing these two is 1. XORing these two is 1. So what we are getting here? 1 1 1 1 0 1 1 1. So from the given options we can choose answer is C. Once again, whenever it is required to convert from binary to gray, in that MSB is as it is, to get remaining bits take XOR of successive bits. So whichever the pairs are there, successive pairs, for those we need to take XOR to get remaining bits. That's what we have done here also. MSB as it is. Right? Then XORing these two successive bits is resulting 1, XORing these two is resulting 1, XORing these two is resulting 1, XORing these two is resulting 0, XORing these two is 1, XORing these two is 1, XORing these two is also 1. So, right, 4 ones 0 1 1. So obviously answer is C for this question. Now let us see next question. Right. This is a logic circuit. Question is, in the circuit output Z is, see, so the output Z is equal to in this circuit. If you are observing this correctly, what we are getting here, it is A C bar whole bar, A C bar whole bar. Here NAND gate output is A C bar whole bar. And what is that other input here? It is A. And what is other input here? It is B. And for this AND gate, what we are getting here? It is B, it is A, it is C. So here we are going to get A, B, C. What is this AND gate output? A and with A C bar whole bar and with B. So logical OR of these two. Let us simplify this. What we get here? A C bar whole bar and with B, logical OR with A, B, C. Then what we get here? A and with A bar plus C and with B plus A, B, C plus A, B, C. So A and A bar is 0 plus here it is what? A, C, right, and with B plus A, B, C. So simplifying to this, A, B, C plus A, B, C. Finally resulting it is A, B, C. So answer is B in the given options. observing correctly, it is an AND gate with A and C bar as inputs, A C bar whole bar, and another input is A, one more input is B. So finally AND gate output is A bar AND with B, and here this AND gate inputs are A, B, C, so it is A, B, C. So if you are simplifying, finally it is resulting A, B, C. So answer is A, B, C. Let us see next question. Following circuit implements A. Observing the circuit, very simple. What is it here? If I say it is I naught, so what is going to be the output of this circuit? Here it is I naught bar A1, and here it is I naught A naught, I naught A naught. So what is the output we are getting here? I naught bar A1 plus I naught A naught. It is nothing but simply if I take here S bar I naught plus S into I1. So a 2:1 multiplexer functionality, if you are observing correctly, if one signal is 0, another signal is 1. So let me say it is I naught, it is I1, and 2:1 mux, and here we have a select line. So what is the output expression? Y S bar I naught plus S into I1. This expression is also resembling that S bar I naught plus S into I1. So it is going to be a multiplexer. It is going to be a multiplexer. So very simple circuit, which is known circuit. A 2:1 multiplexer output is nothing but S bar I naught plus S into I1. Here we are getting that I naught bar A1 plus I naught A naught. So S bar some X plus S into Y. So which is nothing but a 2:1 multiplexer functionality. A 2:1 multiplexer functionality. Now let us see another question which is given in 2017 ISRO EC paper. So what is the value of the register formed from D flip-flops using Q1 and Q2 as outputs, Q0, Q1 and Q2 as output, Q0, Q1, Q2 after 14 clock cycles, after 14 clock cycles. It's a well-known circuit which we generally come across this, which is nothing but in a shift register, complement of last flip-flop output is applied as input to the first flip-flop input, which is a twisted ring counter or ring tail counter or Johnson counter. So what is it here? If you are observing correctly, so output of last flip-flop or complement of last flip-flop output is applied as input to the first flip-flop is resulting a twisted ring counter or ring tail counter or Johnson counter. If I say that 0, 0, 0 is initial, 0, 0, 0 is initial, after a clock cycle what is the state? 1, 0, 0. After one more clock cycle, 1, 1, 0. After one more clock cycle, 1, 1, 1. After one more clock cycle, 0, 1, 1. After one more clock cycle, 0, 0, 1. After one more clock cycle, 0, 0, 0. So finally, 1, 2, 3, 4, 5, 6. After 6 clock cycle, again back to initial state 0, 0, 0. So if it is given 14 clock cycles, after 6 clock cycles, again back to 0, 0, 0. After 6 more clock cycles, again back to 0, 0, 0. That means after 12 clock cycles, it is going to be 0, 0, 0. Right? After 6 clock cycle, again back to 0, 0, 0. After 6 more clock cycle, again back to 0, 0, 0. Means in 12 clock cycle, it is going to be 0, 0, 0. Then 2 more clock cycles, it has to be counted. That means so after 12 clock cycle 0, 0, 0, in next clock cycle 1, 0, 0, and next clock cycle it is 1, 1, 0. It is after 12, it is after 13th, it is after 14th clock cycle. A simple question. We can say that when we are saying that n number of clock cycle, n percentile modulus, you need to calculate n percentile modulus. Then if you are observing that 14 divided by or percentile, what we can say 6 is going to be resulting 2. another way we are analyzing this. So, analyzing each and every clock cycle, or in another way, what is that here? Number of clock cycle must be divided with the modulus of the counter. Then we are getting the remainder. The remainder number of clock cycles you need to count. From 0, 0, 0, if you are counting for 2 clock cycles, it is going to be 1, 1, 0. Another way to answer this question. Counting all the clock cycle, second method is counting modulus number of clock cycles. It is going to be answer 1, 1, 0. Right. So, that is going to be the answer. It is answer A. Now, let us see next question. The 4:1 multiplexer implemented as, then y is equals to, y is equals to. If you are observing this question is also very simple question, S1, S0, S1, S0, 0, 0, 0, 1, 1, 0, 1, 1, S1, S0 connected to B and C. You can say here it is I0, I1, I2, I3. And also here we can have A equal to 0, A equals to 1. If I write combination numbers here, it is going to be 0, 1, 2, 3, 4, 5, 6, 7. So, going through each and every input, I0 is 0 means nothing is required to round off in this. I1 is A bar means A equal to 0 should be rounded off. I2 is A, then it must be rounded off this. I3 is 1 means these two should be rounded off. Is equals to, because it is A bar, it is A, it is 1. So, finally, f of A comma B comma C is equals to sigma m of 1, 3, 6, 7 or 1, 6, 3, 7. Answer is A for this question. Once again, so this is one way of analyzing the given function when multiplexer circuit is given. Another way is, let me write expression here, S1 bar, S0 bar, I0 means B bar, C bar and with 0 plus S1 bar, S0 into I1. So, B bar C and with A bar and with A bar. Now, plus BC bar, because S1, S0 bar into I2, it is nothing but BC bar, here it is A, then plus BC and with 1, so it is BC, it is BC. So, what we get here, f of A comma B comma C, if you write, here we are getting that A bar, B bar, C plus A, B, C bar plus, here we have that BC means A bar, BC plus ABC plus ABC. If you are observing the combinations 0, 0, 1, right, 1, 1, 0, 0, 1, 1, 1, 1, 1 is equals to sigma m of 1, 6, 3, 7. So, answer is again option A, option A. So, we can analyze either this or this. So, when it is very big complex circuit, better to go with this method. If not, we can analyze directly writing Boolean expression of multiplexer output and writing minterms. That is also another way. So, let us see next question. In a digital circuit, the setup time violations can be fixed by. So, what do you mean by that setup violation? When two flip-flops are communicating, let me say here D1, Q1, Q1 bar, FF1 and there is a combinational circuit. Then let me take here another flip-flop which is D2, Q2, Q2 bar, FF2. These two are synchronously clocked. So, let me say it is combinational circuit. So, as per our discussions, right, if it is launching here, it must be capturing here. So, launching data, launching flip-flop is launching after flip-flop delay. Then the changes have been propagated through combinational block and whenever FF2 is expected to be captured at next clock edge occurrence, the data should be arriving setup time early. So if you are getting any changes in the capturing flip-flop, there the changes should be stabilized setup time earlier than clock edge occurrence. So setup is getting violated is saying that if I say that by input is changing from 1 to 0, that 1 to 0 is occurring like this. That 0 is occurring, 0 is expected to capture, but 0 will not be captured because it is violating with respect to setup. So if you are expecting that 1 to 0 change is happening like this, will be accepted. So will be happening like this also accepted. Means it is accepted, but it is not accepted. This is called setup is getting violated. That means the launched data should be captured at next clock edge occurrence, means the input changes should be arriving earlier than setup time at next clock edge occurrence. That means it is violating, means the provided clock period was not sufficient. Setup is getting violated when the clock you are providing is not sufficient for communicating from flop to flop or flip-flop to flip-flop. Communication is not possible in available time period. Then what should I do? I need to increase the clock period to fix the violations, or there should not be any violations, means you need to provide sufficient time for communication. Because of combinational block delays or the requirements of the flip-flops are more, then it may be violating with respect to setup. That is not possible to communicate in one clock cycle is saying that setup is getting violated. So to fix the setup violations, you need to provide more available time for communication. That means you need to increase the clock period. You need to increase the clock period. To increase the clock period, now you need to decrease the frequency of operation. So when you are increasing the clock period to fix the setup violation, the frequency is getting degraded or performance is getting degraded. That is nothing but slowing the clock frequency. Decreasing the clock frequency is nothing but increasing the clock period. Whenever you are increasing the clock period, there will not be any violations. So available time for communication is not sufficient, is giving the setup violation. If you are providing sufficient time for communication, there won't be any violations. To fix the violations, increasing the clock period, decreasing the frequency of clock is nothing but slowing the clock frequency is answer C. For the question, answer is C. Right. Now let us see next question. Number of JK flip-flops in modulo 16 binary up counter are. See, when we are discussing that mod 16 counter can be implemented using minimum 4 flip-flops. Why? So if I say that modulus of counter is n, that should be less than or equals to 2 power n. So the minimum n value which can satisfy this equation is minimum number of flip-flops required to design the counter. So it is modulo 16 should be less than or equals to 2 power n, means what is the minimum n value can satisfy this equation? It is going to be 4. So what is it here? When I am using 4 flip-flops, it is possible to design maximum mod 16. So answer is 4 flip-flops, answer is B. The number of JK flip-flops in modulo 16 binary up counter are. So it is optimal, assuming that it is asked optimal, we are saying that answer is 4. Now let us see next question. Right. This is another question. The circuit is formed as shown below. The output S and C implement. See, here if you are observing the logic circuit, here it is A bar and here we are getting B. And what is that? Here it is A, it is going to be B bar. So finally what we are getting? Yes, A bar B plus A B bar, which is A XOR B, A XOR B. And what about C? It is A bar B, it is A bar B. So if you are observing that a 2-bit subtractor or AB and difference and borrow out. AB can be 0, 0, 0, 1, 1, 0, 1, 1. If I say that A minus B operation, 0 minus 0, difference is 0, borrow is not required. 0 minus 1, borrow is required. Then what is going to be difference? 0 plus base value is 2, 2 minus 1, difference is 1. 1 minus 0, difference is 1, borrow is not required, and 1 minus 1, difference is 0, borrow is not required. If you are observing, difference is equals to A bar B plus A B bar, which is A XOR B, and borrow out, if you are observing, it is A bar B. These are the expressions you are observing in these two. S is giving that A XOR B, C is giving that A bar B, which is nothing but a subtractor, sum is difference, and also here C is borrow out. So answer is B for this question. Right. Next question. Right. Simplify the Boolean expression. F of W x y z is equal sigma m of 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. Let me take a K-map to simplify this. Variables are W x y z, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Then what we are getting here? 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. These are minterms. Then if you are simplifying, it is going to be an octave, then it is a quad, and it is also another quad. Then let me write a simplified expression. So in this octave, y equal to 0 only, not changing, y bar, plus in this quad, w bar and z bar, w bar and z bar. Why? Here x is changing, w equal to 0 is not changing. In this, if you are observing, y is changing from 0 to 1, z equal to 0 is not changing. Plus another quad, if you are observing, in this x is not changing, x equals to 1, and z equal to 0 is not changing, x z bar. So finally y bar plus w plus x z bar. So if you are observing, option is B. Y bar plus w bar z bar plus x z bar. That is the answer for given question. Next, let us see next question. Which of the following is an example of oversampling ADC architecture? So oversampling architecture, we are seeing that in sigma delta only. In the remaining, we don't have that oversampling. So only in sigma delta ADC we have that oversampling. So answer is A, sigma delta. Right. Now let us see next question. Right. So which of the following statement is correct? If you are observing, simply NAND and NOR is given, or commutative or associative. Is very simple question which we know already. So which are associative, which are not associative. So already we have seen that how to implement that higher order using lower order, which is possible or not. So if you are observing that AB whole bar is equals to BA whole bar, and also A plus B whole bar is equals to B plus A whole bar, which is saying that, right, NAND and NOR are commutative, but they cannot be associative. Why? AB whole bar and C whole bar is not equal to, right, A BC whole bar and again bar. So it cannot be associated. Why? Here we are getting that AB plus C bar, here we are getting that right, A bar plus BC. These two cannot be equal. These two cannot be equal. So associative property is not satisfied by NAND and NOR. So these two are satisfying commutative. So correct option here is so NAND and NOR functions are commutative but not associative. Answer is D for this question. So let us see next question. Which of the following digital devices requires an external refresh? It is also direct theory question. If you are observing, a DRAM is changing the logic over a period. So if you are observing a capacitor with a MOSFET, so it is a oxide and poly. So let me say that I am not applying any logic here. There is a capacitor. Capacitor is fully charged. And if I say it is P substrate, then it is grounded. So what we assume that it is not created any channel, means the charge in the capacitor remains same. The logic which is stored in the capacitor is same. That's what we are assuming. But because of reverse biased PN junction here, which is having a reverse saturation current, because of this there is a leakage. Whenever it is moving from VOH to VIH, once it is crossing that VIH, there you need to refresh the logic. Whenever it is decreasing the potential across the capacitor, because of this leakages, when it is dropping below VIH, then it may be into forbidden or it may be becoming logic 0. In that cases, you need to refresh the logic. For that we are using additional circuitry or external circuitry. So answer is DRAM, in which it requires additional refreshing circuit or external refreshing circuit. Now let us see next question. What would be the maximum operating frequency of mod 8 counter constructed with JK flip-flops having propagation delay is 8 nanoseconds? If you say that mod 8 means we require 3 flip-flops. So if you are observing that T minimum is equals to N delta. So it is nothing but N 3 flip-flops, delta is 8 nanoseconds, it is going to be 24 nanoseconds is the minimum clock period ideally. Now if I say that maximum clock by T minimum is nothing but 1 by 24 nanoseconds, it is equals to 0.041666 so and so is gigahertz. Then it is equals to 41.66 approximating to 7, which is megahertz. So it is going to be 41.667 megahertz. Now let us see next question. An SRAM has address lines from A0 to A19 and data width from D0 to D15. Is saying that address lines is 16, address lines is 20 and data lines is. If you are observing that memory 2 power m into n, that means 2 power 20 into 16. 2 power 20 is mega, because 2 power 10 is kilo, 2 power 20 is mega. So it is 2 megabytes, because it is written as 2 into 2 power 20 into 8. So it is a byte, it is mega, it is 2 megabytes. So answer is A for this question. Now let us see next question. The logic function implemented by following circuit can be represented as. It is also very simple question. If you are observing, these two are in series, which is nothing but AB, and if you are observing this one, what do we have here? It is A, it is C. So what is it here? We are getting A plus C. So they are in parallel, it is A plus C plus A plus C. And after that, this circuit, if you are observing, what do we have here? It is A, it is B plus D. So plus, because they are in parallel. So A and with B plus D whole bar. So what we can say here? A B plus A plus C right? Plus we can write here, it is a B plus D. So AB plus, just a minute, here it is A and with B plus D. So AB plus AD, AB plus AD. So what we get here, it is AB plus AB is AB plus A plus C plus AD whole bar. So finally what we get here, it is AB plus A plus C plus AD whole bar, answer is D. Observing correctly, AB are in series, A and B, and here if you are observing, here A plus C, because these two are in parallel, this network is in parallel with this. So plus A plus C, and here if you are observing, here we have A, here we have B plus D, A and with B plus D. If you are simplifying, AB plus A plus C plus AD whole bar. So that's what we are getting. And here in pull-up network, if you are observing, there is a diode connected transistor which is always on. So finally, it is NMOS logic is used, and logic function if you are observing in pull down network, the logic circuit if you are observing, answer is AB plus A plus C plus AD whole bar, answer is D. Here we tried most of the questions from previous ISRO exams, ECE as well as EE, right? All the best for your coming exams.